Alrighty, so let's continue our discussion about the finite square well. Last time we went through Schrodinger's equation for the finite square well. Remember, the potential piecewise definition was when x is less than 0, the wall, the potential, is some finite value, v naught, for x less than 0. It's 0 between 0 and a, and it's back up to v naught again for x greater than a. And if we draw it out, it looks like this. This is the position, this is the potential at 0, and to the left of 0, the wall is at v naught. And at a, the wall is at v naught again. So all of this is wall, all of this is wall, and we put a particle in here. And we're assuming our energy is less than v naught. Okay? We could do a different calculation where we assume the energy is greater than v naught, but for now, this is what we're working with, less than v naught. So we did this, that is region 1 is here, region 2 is here, and region 3 is over here. And we found the wave functions, psi 1, or psi in region 1, psi 1, is a e to the kappa x plus b e to the minus kappa x. Psi 2 was c sine kx and d cosine kx. And in region 3, because we have to skip e, because e means energy, f e to the kappa x plus g e to the minus kappa x. Okay? So we found this last time. Our job today is to start working with the boundary conditions and see how far we can get with this. So first, let's discuss boundary conditions. The first set of boundary conditions I'm going to talk about are kind of hidden. They're not the natural ones we would get if we were just doing a pure mathematics course. In mathematics, remember that the differential equation that this is the answer to is a second order linear differential equation. That is to say, minus h bar squared over 2m, second derivative of psi with respect to x squared, plus v naught psi is equal to e psi. So first of all, it's a linear differential equation because there's no terms that are squared. So that it's the second derivative, but it's not the derivative squared. It's the second derivative. And it's not psi squared anywhere. So it's a linear differential equation. Second, it's a second order linear partial differential equation because the highest derivative term is a second derivative. So second derivative means second order. And there's a rule in mathematics, a rule of differential equations, that says that the number of boundary conditions you need to completely solve a second order or a differential equation of order n is n. So if you have a second order differential equation, you need 2 boundary conditions. If you have a first order differential equation, you only need 1 boundary condition. Okay? So math would tell us, because this is a second order differential equation, I need 2 boundary conditions to solve this. And of course, because I had to split it up into 3 regions, that means I need 2 boundary conditions on each region. It's still just 2, although it seems like it's 6, because 2 for 1, 2 for 2, 2 for 3. That's a total of 6 different things. But really, it's the same 2 boundary conditions. We're just using them 3 different times. However, we're physicists, and we're working on a physical system, and there's 2 other conditions we're going to have to work on. I'm going to call them boundary conditions. Whether you think of them as boundary conditions or not, that's up to you. That's just parlance. But there are 2 more conditions, and I kind of hinted at them at the end of the last video. These conditions say this. In quantum mechanics, if we have a wave function of a physical system, then there's a rule that says that the wave function when you try to calculate it, at infinity must go to 0. That is to say, when you try to look for a particle, because that's what a wave function is telling you, if you square the wave function, is the probability of finding the particle. If you try to find a particle infinitely far away, it's not going to be there. It has to be somewhere here in the universe. So let's look at these and use that rule, that condition, on our wave functions to see if we can eliminate some stuff. So let's look at region 3 first. This is the easiest one to see. For region 3, if I were to draw it, we're just looking at the right side now. Okay, remember there's other stuff over here. We don't care about all this stuff. But region 3 is a wall that goes this way, and this is x, and that's going infinitely far to the right. Let's look at our wave function. Our wave function in region 3 says it's the sum of two terms. One term, the g term, is e to the minus kx, or e to the minus kappa x, I'm sorry. Well, an exponential with a negative means it's an exponential decay. So let's say, for now, inside the well over here, we had our wave function is a nice wave, and it goes up to here. One thing we know, first of all, this is going to be part of our boundary conditions later, is that the wave function has to be continuous across a boundary. So that means on the right side, in region 3, this is region 3 here, the wave function has to continue where it stopped. So it stopped right there. Okay, so it's going to continue from there. Well, we have two terms. One term is an exponential decay. So we'll make that look like this. Exponential decay looks down like that until it goes down to 0. So that's the g term right there. That's not g, I'm just calling it the g term, okay? Make sure you understand that. The other term, the f term, is exponential growth. E to the positive kappa x means it's getting bigger and bigger. So it starts from the same starting point, but now it's growing and growing and growing. Okay? So that's the two terms. And the actual wave function is the sum of these two things put together. Okay. Now we use our physical condition here. We know that the further to the right we look, as we get to infinity, way to the right, the wave function has to go to 0. Well, the g term, that's perfectly fine. Notice the g term is going to 0. The further to the right we go, e to the kappa infinity with a negative, e to the negative infinity is just 1. It's going down, it's just 0. I'm sorry. You're getting less and less and less down to 0. So he's good. But the f term, this guy here, notice that guy, as we go further and further to the right, he's getting bigger and bigger and bigger. So when we stick infinity into x, e to the positive infinity is infinity. That would tell you that if you stuck a particle in this well and you waited a while, eventually, if you look to the right infinitely far away, it's an infinite probability of finding a particle over there. That can't be true. So that tells us that term that does not eventually go to 0 at infinity cannot be there. So that means the f term has to be 0. So we've just gotten rid of that whole term. The g is still there. The g term is perfectly fine. We don't know how to mess with him yet. He satisfies our condition. But the f term does not. All right, now we look at region 1, and we do the same kind of a thing. Region 1, very similarly, looks like this. Remember, this is the wall over here. All of this is wall to the left. We don't care what's going on the right now. We're just looking at region 1. And we say, okay, this is slightly awkward because things are backwards, because now we're going to deal with negative numbers, but the same kind of a thing is going to hold. Look at the first term, the a term. When we stick x's in, the x's we're going to stick in start at 0 and go less and less and less, more and more negative. So when we stick e to the minus infinity, and again, we have a particle somewhere in our well, and he's here, and he ends there, let's say. When we stick the a term in with negative numbers, that's the same as saying e to the negative kappa x, he's going to go with exponential decay. Okay, so that's the a term. It's kind of weird because it's a positive exponential, but you have to remember that in this region, all of our x's are actually negative numbers. So it's really an exponential decay when we plug the numbers in. Whereas the b term, e to the minus kappa x, when we stick negative x's in, the negatives cancel and we get exponential growth. So he shoots off to infinity like that. That's the b term. And likewise with region 3, if we look infinitely far to the left, to negative infinity, our wave function again has to go to 0. Well, the a term satisfies that. The more we look to the left, the closer it gets to 0. We're perfectly fine. But the b term, as we get closer to negative infinity, this thing's blowing up to positive infinity. That's bad. We can't have an infinite probability out there. So again, that term goes to 0. Okay. Now what about region 2? Well, region 2 we don't have to worry about for this condition because region 2 is in here somewhere that never goes to negative infinity or positive infinity. We're stuck between 0 and a, so this condition's not going to apply in there. We only have to worry about this type of physical condition when we're in a region that could potentially go to negative or positive infinity in space. Okay, so region 1 does, region 3 does, but region 2 for this particular problem does not. And that's why we didn't worry about this in the infinite square well. In the infinite square well, we ignored region 1 and 3 because since the walls were infinitely high, we could never be there. We were stuck to be inside the well, and so we never worried about, well, what happens if we go to positive infinity or negative infinity? Now we do have to worry about it, and so now we have to satisfy those conditions. So with that said, now we have a new set of wave functions, a more updated, I should say. Region 1 is now a e to the kappa x. Region 2 is the same as it was before, c sine kx plus d cosine kx. And psi 3 is g e to the minus kappa x. All right, so that's our updated wave functions. We've already eliminated 2 unknowns, b and f. Now our job is to try to eliminate the rest, the a, the c, the d, and the g. So now we have to do boundary conditions, the normal differential equation boundary conditions for this. So what do the boundary conditions look like? Well, we had a skewed view of the boundary conditions when we did the infinite square well. If you remember for the infinite square well, we said the boundary conditions, and I'll just draw it really quick. This is infinity, all of this is wall, all of this is wall. The boundary conditions were that you could have some wave in here, but the wave had to go down to 0 at the boundaries, right? And so we said the boundary condition was psi 1 at x is equal to 0 at the boundary must be 0. And psi at the boundary x is equal to a must also be 0. Remember, those were the boundary conditions. Now, that was kind of a shortcut boundary condition. I kind of hid from you what the true boundary condition means. So all of this is infinite square well. Actually, the real boundary conditions go like this. And this is true always, even for the infinite square well. Real boundary conditions say this, and I kind of did it all over here already. Real boundary conditions say when you reach a boundary, the wave function on one side of the boundary has to match the wave function on the other side of the boundary. So notice in my region 3 drawing on the bottom right here, I've got my yellow wave. That's like the particle inside of the box. And he's moving along to the right. He hits the wall. He hits the boundary. Well, at that point, at that boundary, the wave function in region 2 must equal the wave function in region 3. And so this little point right here is where they equal. Now, once you get past that point, they could start to move away from each other. They could diverge from each other. But at the boundary, they're the same. And the same is true for region 1 over here. Notice. Again, the yellow is the wave that's inside of the box. He's moving to the left. He hits the wall. At that point, the wave function from the right must equal the wave function on the left. That is, the wave function in region 2 is the same as the wave function in region 1. Okay? Now, I didn't say that here for the infinite square well, but I kind of did in a roundabout way. What I said there was the wave function when it hits the boundary is equal to 0. The reason these are the same thing is because I didn't tell you, but we still have 3 wave functions. Wave function in region 1, region 2, and region 3. It's just that the wave function in region 1 is 0. You're not in that wall. And the wave function in region 3 is 0. You're not in that wall either. So if it must be that the wave, when it reaches a boundary, has to be equal on either side, and on one side it's 0, that means region 2's wave function better go to 0 as well at the wall on either side. Okay? So really, the true boundary condition says this. And we'll start with the first boundary. And I'll go ahead and draw what this looks like. I have region 1, region 2, region 3. This is the finite square well now. Here's 0, here's A. It says that the wave function in region 1 at the boundary, x is equal to 0. So this is the boundary right here, the wall, where the wall starts, better be equal to the wave function in region 2 at the boundary, x is equal to 0. So if there's some wave in region 1 and some wave in region 2, when they meet at this wall at x is equal to 0, their location, their position, their height, the height of this wave is the same. Their value is the same. And that's what this says here. Okay? There's a second condition, which we didn't worry about for the infinite square well because we didn't need to. But the second boundary condition says that not only does the wave function have to equal at the boundary, but the derivative of the wave function has to be equal at the boundary. So that says the derivative of the wave function for region 1 with respect to x, setting x is equal to 0 at the boundary, better be equal to the derivative of wave function in region 2 with respect to x at the boundary, x is equal to 0. Okay. So there's my 2 boundary conditions. So for the left part, that is this left wall here, this boundary, x is equal to 0, you have 2 conditions. The first condition is that the wave function must match on either side. So that is psi 1 at x is equal to 0 is equal to psi 2 at x is equal to 0. Also, the derivatives have to be equal as well. So the derivative of psi 1 at x is equal to 0 must be equal to the derivative of psi 2 at x is equal to 0. But notice we have a second boundary. We have 2 walls here. Well, the same conditions better hold at the other wall too. So what's going on at the other wall? Well, you have wave 2, wave function 2, sitting here, hits the wall, and it has to meet up with wave function 3. So we have psi 2 at the boundary, x is equal to a, better be equal to psi 3 at the boundary, x is equal to a. Okay, just like the first one, it's just that now we're on the other wall. The first wall has region 1 and region 2 meeting. The other wall has region 2 and region 3 meeting. Okay? And then likewise, same with the derivatives. The derivative of psi 2 with respect to x at the boundary x is equal to a is equal to the derivative of psi 3 with respect to x at the boundary x is equal to a. Okay. So again, we have a second order linear partial differential equation. Second order tells us we need two boundary conditions to solve it. So we have two conditions. The wave functions are equal and the derivatives are equal at the boundary. But we have two boundaries, so that same two conditions holds for the left boundary and the right boundary. Notice that gives us four equations, four different conditions. Well, how many unknowns do I have sitting in my wave functions? I've got A, C, D, and G. Perfect. I've got four unknowns and I have four equations. That's exactly what we need. Of course, really I have five unknowns. If you don't remember, stuck inside kappa and K is the energy E. The energy, the allowed energy, is also an unknown. So really there's five unknowns, but we only have these four conditions. But remember, we do have a fifth, and that's the normalization. We have to normalize the wave functions once we get all of this done, and that'll give us our fifth unknown. So, how many unknowns do we have? We have five unknowns, the four constants here, plus the energy. And how many equations do we have? The four boundary condition equations plus normalization. So this is a solvable problem. That's good news. The bad news is actually solving it is not easy. We could do a lot of algebra coming up, and we will do a lot of algebra with these boundary conditions. However, inevitably, I'm going to tell you right up front, unlike the infinite square well, where we were able to do all the boundary conditions, then we normalized it, and then we got a final wave function and a final allowable energy levels. Here, although we have enough equations for our unknowns, we're going to arrive at a final equation that's a transcendental equation. Transcendental. A transcendental equation means it's an equation which cannot be solved by hand analytically. There's nothing you can do, to the best of any mathematician's knowledge thus far, that will let you solve that problem. We can solve it in a way. We could stick it on a computer, put numbers in, and get a numerical answer, which we can get as accurate as we want. However, I won't be able, when I get my final equation coming up, to write something like psi is equal to, square root of 2 over a sine n pi x over a. I won't be able to do this. I could do it for the infinite square well, where I get an actual physical answer, analytical, that I could write down, a function. However, for this problem, the finite square well, what makes it more difficult is that no matter how hard we're about to try, we're going to wind up with a final equation that we're going to be stuck with. And we cannot go any further without a computer. But we have to get to that point. So we're not done here. All right. So let me show you the first two boundary conditions, and then I'll leave the other two for you to do yourselves. But I want to show you because there's a little trickiness about to happen here. Okay? A little trick you're going to have to be sure you're aware of. So let's try to solve these boundary conditions. The first boundary condition, if you remember, said psi1 at the boundary x is equal to 0 better be equal to psi2 at the boundary x is equal to 0. And let's remember what psi1 was. Psi1 was a e to the kappa x, and psi2 was c sine kx plus d cosine kx. Okay. All right, so let's do this one. Here's the, well, for this one it doesn't really matter. Let's go ahead and plug everything in. All right, psi1, where we plug x is equal to 0. Okay, a e to the kappa times 0 is equal to psi2 when x is equal to 0. C sine k times 0 plus d cosine k times 0. All right, now let's simplify it. Let's see where it leads. E to the kappa times 0 is e to the 0, and e to the 0 is just 1. So on the left side we have a. On the right side, sine of 0, or sine of k times 0, is 0. Sine of 0 is 0. So we have c times 0, well that's just 0. And then we have d cosine k times 0. Well, cosine of k times 0 is cosine of 0, and the cosine of 0 is 1. So d times 1 is just d. So we get a is equal to d. There we go. So I've now used my first boundary condition, and what did I discover? I discovered that a is the same number as d, whatever that is. I don't know what the number is, but whatever it is, they're the same. All right. Next boundary condition. Now I have the derivative. Now, I'm going to do a little weird notation here. It's just what I'm used to, and I'm going to explain it to you. When I write, of course, we have the partial derivative of psi with respect to x. I can say it's the same thing as writing the partial with respect to x of psi. Okay, it's just shorthand. So you don't have to write it as a fraction every time. Okay, so the partial derivative of psi with respect to x is dx psi, like that. So the partial of x of psi at x is equal to 0 for region 1 is the same as the partial of psi 2 at the boundary x is equal to 0. Let me go ahead and box this for now. Okay, so the derivatives have to be equal at the boundary. Now, here's the big trick. Here's something you have to be very careful about. There's two orders. One of them is right, one of them is wrong. Because if you notice with the first condition, I had to set x is equal to 0. Here, I have to take derivatives, and I have to set x is equal to 0. The order is you take the derivatives first. After you take all the derivatives, then you insert 0 in for x. Okay? It's tempting to set x is equal to 0 first, but if you do that, notice what happens. Just as a little quick thing. If I take the derivative of psi 1, well, first, let me plug x is equal to 0. I get a e to the kappa 0, right? Well, that's just a times 1. And now I need to take the derivative with respect to x of that, but there's no x. X has gone away, so this is just 0. This is wrong. You cannot insert x is equal to 0 first. You have to take the derivatives first, then after that, you plug x is equal to 0. Okay? I know it's funny to say it, but you see this mistake happen a lot. Even on more complicated systems where it's not as obvious you can't do it. Here it's obvious you can't do it, but you still need to see, don't do it. So, first we take derivatives. All right? psi 1 derivative, well, what do we get? Well, we get the a stays there. Derivative of an exponential is the same exponential. And now chain rule tells us we have to take the derivative of the power. Derivative of kappa times x is just kappa. All right, so there's the derivative. Now I'm going to be setting x is equal to 0. And I just put that in to remind me. On the right side, same kind of a thing. The c is there. I have to take the derivative of sine kx. The derivative of sine is cosine kx. Then chain rule, the derivative of the inside of the cosine, the derivative of kx is just k. All right, plus the second term, d, is still there. Derivative of cosine is minus sine kx. And then chain rule gives me an extra k. And again, I have to set x is equal to 0 here. So what do we have? Now I'm going to plug my x is equal to 0. I've got kappa times a. Then I have e to the kappa 0. E to the 0 is just 1, so this is just kappa times a. On the right, now I'm plugging x is equal to 0. Well, I've got k times c. X is equal to 0. Cosine of 0 is 1, so the cosine goes away, and it's just k times c. Minus k times d. Now I stick x is equal to 0 here. Sine of 0 is 0. Ah, that's nice. So this term is just 0. All right, and now I'll do a little cleanup here. And we could say, let's solve it for c. I don't know why. We solve it either for a or we solve it for c. It doesn't matter. I'm going to solve it for c. So I find c is equal to kappa over k times a. Now be careful. It's very, very easy to confuse kappa and k. I hate that this is the notation that's standard, because kappa and k, especially when you're writing quickly in your notes, can look very similar. But one is capital, or one is like a curly k, and the other is lowercase k. But there we go. There's my second boundary condition done. Again, I don't know what a, c, or d are, but I have some relationship between them. I know that whatever a is, it's the same as d. And I know that whatever a is, c is that a times kappa over k. Okay? Now, the next step, which is what I want you to do, is the two other boundary conditions. Psi in region 2 at the new boundary, x is equal to a, is equal to psi of region 3 at x is equal to a. And the derivatives. Derivative of psi 2 at x is equal to a is equal to the derivative of psi 3 at x is equal to a. Okay? Very similar to how we did these two, only now you're working with psi 2 and psi 3 instead. And what you're going to find for these two is it is more complicated, because with these, the first ones, putting x is equal to 0 makes a lot of things cancel out and a lot of things simplify down. When you do these two, you're sticking x is equal to a, and now things won't cancel out anymore. You're going to have e to the kappa a, you're going to have sine ka, you're not going to have zeros and ones and things anymore. But that's all right, it's not a big deal. You just have to be very careful and organized with the algebra. Once you have these two, you're going to have a whole bunch of relationships between A, D, C, G, F, all of them. Or not F, F's gone. A, C, D, and G. What you want to do is here in these two, you found D in terms of A and C in terms of A. Okay? So when you go to these, you're going to have C and D with G, and C and D with G. replace the C and D with what they are in terms of A. So let's say for the first one you have something like, I don't know, C sine Ka plus D cosine Ka is equal to G e to the kappa A. Okay? Then C, instead of writing C, you write what this thing says. Kappa over K times A sine Ka. And instead of writing D, same thing. You write what this thing says instead of D. So you're going to have a whole bunch of A's on the left and G on the right. Solve this for G equals blah, 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 A. Then do the derivative one. Again, you're going to have C with cosines, D with sine. You're going to have a G. There's kappas, there's Ks, all sorts of stuff you're going to find. Again, replace the C, replace the D, just like you did before. And then you're going to have G in terms of A, plug that G into this G here. When you do that, you're going to have one big long equation, but all of the A, C, D, and G cancel out. And you're just going to have cosines and sines and exponentials, kappas and Ks. Okay? That's your final transcendental equation. That's the thing that has to be put on a computer. You will not be able to go any further than that by hand, which is fine. So I just wanted to preview what to expect, because that's going to happen. It's going to be a little bit more complicated than these two, only because it looks messier, because you don't have everything canceling out as easily. So just be very careful. Think about what all these terms are. If you want to make substitutions, like if you wanted to say let, kappa over K e to the kappa A equal, I don't know, gamma. So every time you see this thing, because kappa, K, A, those are all just numbers. They're not the C, the D, or the G, or anything like that. They don't have X in it. So you can just call it a constant. I mean, after all, that's what kappa and K are. They were originally, the 2m over h bar squared times v naught minus e and all that stuff. So you're just going to reduce it so everything looks a little prettier, if you want to do it that way. If you don't want to do it that way and you just want to leave everything dirty and complex looking, that's fine too. But if, when you plug everything in and you make all your substitutions, all of the C, D, G, and A's don't cancel out, then you did something wrong. They better all cancel out. So if they don't, look back and see what mistake you might have made. If they do all cancel out, then probably you did it right. Perfect. We'll continue from there. Okay? So that is the boundary conditions for the finite square well. Okay? Next time I'll show my solution, what it looks like when I do all the algebra myself and I get down to the final transcendental equation, and then you can see if it matches your result. Another thing to worry about here with transcendental equations is sometimes you could have two different transcendental equations that are actually the same, even though they look different. Okay? Because maybe you made substitutions different than I made. Or you called it tangent and I used cotangent somewhere or something. Because remember, we have cosines and sines and things are going to be divided and all sorts of stuff. Don't worry too much about that. Where you would worry about this is once we plug it into a computer and try to solve for what are the allowable energies, those better match the actual energy levels. But what the final transcendental equation looks like, you might have three different ones that are all looking different, but all mean the same thing. Okay? All right, so anyway, that's all I have for this one. I hope it makes sense. Practice the heck out of this. The algebra can get a little messy. You have to stay very, very organized. Give yourself lots of room. Make sure you're following what you're doing. and things should go okay. If you have any questions, of course, let me know, and I'll see you next time.